Okay, let's talk about what is an eigenvector, what is an eigenvalue, and how you can find them using a little neat formula and why this works. So we know when a matrix acts on a vector, most vectors get mapped in some strange way, but a few, called eigenvectors, will only get mapped to a scalar multiple of themselves. So these x, this is what happens. The x is an eigenvector. The eigenvalues are lambda eigenvalues. These are the lambda guys here. So they are the scalar multiple of the vector. And after you accept that definition, that's all well and good. So each matrix, each linear map A, will have eigenvalues possibly. It's actually easy to prove if your linear map is acting over an algebraically closed field, that there is always at least one eigenvalue. Okay, so when you're given linear maps, especially in physics and all sorts of applied maths, you are quite often looking to find these eigenvalues. So there's a really neat way to do that. So I want to intuitively derive why this works. So if you consider your matrix A, X, and we just move this lambda here over to the left-hand side, like here. So this is going to be equal to the 0 vector. Now, what I want to do now is think about a really cool way of thinking about this. So we have a matrix times a vector here, and we have a scalar times a vector here. I would rather write this as one matrix, and you can convince yourself that lambda times the identity will act on x to give lambda x, because the identity times the vector x is just going to give you x. So this works. This step might seem a bit strange, but now what I have is a specific matrix that I can start thinking about to consider the eigenvalues. So we know that for the lambda that actually are eigenvalues, this vector x gets mapped to 0 under it. Okay, so if we just consider these matrices for a second, I'm gonna give these guys a name. Maybe what we're looking for is the set of all vectors that get mapped to 0 under the action of these matrices. And in mathematics, we call that the kernel. Okay, you may be familiar with that. But the kernel is just all the set of vectors that get mapped to 0 under the linear mapping. Okay, so what we're really looking for is any vector in the kernel of this guy here. So this is interesting. So really, what this thing is a specific idea on how to find these eigenvalues. So I'm going to define it, because I'm going to give it a name, because we're going to talk about it a lot. It's going to be used a lot. This is called the eigenspace. Okay, so the eigenspace is the kernel of this guy. So basically the eigenspace is all the vectors that are actually eigenvectors. So remember, for the vast majority of lambda, most lambda will not satisfy this equation. Okay, so the kernel will be trivial, right? So the kernel, or the eigenspace, the kernel of this matrix is usually going to be 0 for the vast majority of lambda, but for specific lambda, it may be non-zero. And in that case, there will be some vectors in the kernel. Okay? So what we're really interested in is the lambda for which there exist vectors in the kernel of this matrix here. Because if that's true, these vectors will get mapped to 0 under its action. And then, of course, they turn out to be eigenvectors. Okay? So x belongs to the kernel of this guy. Specifically means that it is an eigenvector. And the lambda such that the kernel is non-trivial means that they are eigenvalues. Okay, so the question is there an easy way to find these lambda? Well, yes, because what do we know? We know that when the kernel of a matrix is non-trivial, we know that the determinant is 0. So the only way to consider the eigenvalues, or rather one really good and optimal way, is to consider when the determinant of this matrix thing is 0. Okay? For what lambda is the determinant 0? So for what lambda is the kernel of this guy non-trivial? Remember, non-trivial just means it has other stuff in it apart from 0. So setting the determinant of this equal to 0 will give us precisely the values of lambda that make it 0, which give precisely the eigenvalues. Okay, it'll give us precisely all the vectors that actually get mapped to a scalar multiple of themselves. This is a pretty hard concept to get your head around at first, but this equation, the characteristic equation of a matrix, will give you the eigenvectors out exactly. All right, I'll go through this one more time. To find the eigenvalues and eigenvectors of a matrix, you consider when the determinant of this guy here is 0. And if the determinant is 0, what that means is the kernel is non-trivial, which means that there's some vectors in it, apart from the 0 vector, and these vectors are the eigenvalues. Okay, because when they're in the kernel, this times this is 0. Yeah. So that's it. That's really the way I think about it. That's the way I think about it.